Hi, my name is Ingvar Stepanyan. I'm a WebAssembly developer advocate at Google, and you can find me as Aragarsa on Twitter, GitHub, Instagram, wherever. And I'm always happy to help with any WebAssembly related questions. Probably not on Instagram, so. And today I'm going to talk about Asyncifying WebAssembly for the modern web. Let me start by explaining what it is and why developers should care about Asyncifying their code. Let's say we have a simple hello world example in C. Here we try to print a string to the standard output, and when this code is compiled with Async and executed, all goes well, and you see the expected output in the console. Things remain relatively simple for a lot of use cases, particularly library ones, where you might be getting some numbers or binary data as an input, crunching it by performing calculations or parsing or whatever, and returning the results back to the caller on the host. However, what if we are building an application and not a library? In this case, instead of accepting a prepared input data via parameters, we need to handle all the input-output communication with the output world ourselves. That is, if we want to be able to do anything useful beyond just login. To extend the login example while still keeping it simple, let's say we want to read users' names from a file and read them instead of world. In order to do that in C, you need at least two crucial I/O function calls: fopen to open the file and fread to read some data from it. One thing that is remarkable, or depending on what you're used to, maybe unremarkable about those calls, it's how you just invoke the functions and get the result back synchronously without thinking twice of all the time-expensive machinery involved in order to allow you to perform such reads from either the hard drive or maybe even a mounted network drive or anything addressable by your host file system. If you try to do it in Rust, the API might be simpler, but the same principle applies. You just make a call and wait for it to locate the file, check its permissions, open it, read data block by block, and close it and return the result back to you. And some will correct me that by saying that Rust has asynchronous APIs today, but let's leave them out of scope right now, just for simplicity. Finally, WebAssembly has an emergent standard for I/O syscalls called WASI. It was designed specifically for console applications, but at least for now, it remains the only de facto standard for compiling any I/O from other languages to WebAssembly. As such, it's also interesting to take a look at. If you look at the definition of FTF-read, the system call it uses for reading data from a file, we can see that just like in the earlier shown higher-level languages, it also performs the I/O synchronously and returns the result back in the provided buffers. So no surprises here. The reason I'm pointing this out in all these different implementations becomes clear when we think about what this code in either of the proposed languages is supposed to do on the web. Or as in our particular example, what would fread actually do and map to? Unlike code running on a real file system, the web has a variety of different storage options. Files can be saved in some sort of an in-memory storage. In the simplest case, literally a JavaScript object mapping from file names to their contents. In this case, the caller would be responsible for pre-populating the map with input files, and the compiled WebAssembly application can read them, modify them, create new ones, delete them, whatever. This works pretty well and is, in fact, the default file system option in Emscripten. But it has the obvious downside of losing all your data upon tab close or reload. Another alternative could be something like local storage. It's a browser API for key value storage that allows to store and persist data across visits. The downsides are that it can only store strings, so you need to serialize any data, and it can be slowish to work with, and it's limited in size, where the limit is different between different browsers and origins. There are some complicated rules that I won't be covering here, but it's generally under a couple of megabytes per website. Then there is IndexedDB, which is kind of similar to local storage and falls under the same size limits, but allows you to persist some structured data, including binary blobs. As a downside, browser is allowed to delete your whole database when systems you've just used too much of storage or don't need it anymore. Then you could map file reads to network requests, where the actual data lives somewhere on your server. In this case, you can store anything as much as you want, as long as you want, but you pay the obvious cost in latency. Finally, there is a new native file system API, which allows you to store data on the actual file system. This way, avoiding pretty much any limitations as well, but it's still worked on and available only in Chrome and Chromium-based browsers. But the interesting thing about all of these different options is that only two of them, the in-memory storage and the local storage, provide any sort of synchronous access. And both are the most limiting in what you can do. This is one of the core properties of executing code on the web. Any expensive operation, which includes any real I/O, has to be asynchronous. The reason for this is that the web was historically designed as single-threaded, and any user code that touches the UI has to share the same thread as the UI and compete with layout, rendering, and event handling for the CPU resources. It would be highly undesirable for a piece of JavaScript or WebAssembly to be able to start a file read or network operation and block everything else, the entire tab, or in the past, the entire browser, for a range from milliseconds for local file access to seconds or even tens of seconds for network access. Instead, code is allowed and encouraged to start an I/O operation and then schedule a piece of another code to be executed once it's finished. For example, if we were to reproduce samples above in JavaScript and decided to read a name from a remote URL, we would use Fetch API to start a request and subscribe to its finish with a callback. Once we got the initial response, just HTTP headers, we can once again asynchronously ask for the body in text string, and then subscribe again with another callback. And once we got the contents back, continue execution and print our greeting. This way, the original function can return control to the browser once the I/O has been scheduled, and so the entire UI remains responsive and available for other tasks, including rendering, scrolling, any user interaction, and so on. In a modern syntax, the JavaScript code above can be rewritten using a feature called async await, which makes it easy to read and look almost like synchronous examples, but still does exactly the same under the hood. It suspends the function mid-execution, subscribes to the I/O result, returns control to the browser, and later continues execution only once we got the result back. All of it without blocking the main thread. The way asynchronous operations work on the web or in Node.js is through a mechanism called an event loop. In essence, as the name implies, it's just a loop that goes through and handles incoming events. But the specific model and order of handlers might be hard to keep in mind. I definitely know it does. So I made my best to draw a flowchart that demonstrates it. First, we execute the provided entry code. Then the code might have scheduled some microtasks. The most common kind of those is something like promise callbacks, which need to be always executed asynchronously, but also as soon as possible. And so they're being handled fastly, right after the original JavaScript. If they schedule more microtasks, those will be handled as well, until we exhausted all of them. Once we exhausted all the microtasks, we check if there are any macro tasks or just tasks. Those are callbacks or handlers to the real external I/O APIs, like timers, file access, and so on. This time, we also check the microtask queue after running each of those handlers, as it might have scheduled some more, until we run out of both. Finally, once we run out of both, we check if there is any I/O in progress and give up control until it resolves. In a browser environment, there's always something potentially coming up, like just user clicking around or scrolling or whatever. So this part doesn't make as much sense. But in Node.js, you might actually handle all the asynchronous tasks you schedule, run out of them, and then the program will exit. What's important to remember about this mechanism is that your user code can execute in a couple of places before anything happened, as a response to a microtask or as a response to a task, I/O. It's often also called a blocking code because while it executes, the event loop is blocked and there's no way to react to any external handlers, events, I/O, etc. The only way to handle anything external is to register a handler, finish executing your code, and give the control back to the event loop so that it could wait and handle any pending tasks. On practice, I've seen this creating some confusion to developers coming from languages with typically multi-threaded environments. For example, one might expect to be able to share some state with a thread during the I/O and wait for it to be updated by repeatedly checking the state. This is usually called polling mechanism. Like in the example above, someone starts a fetch, subscribes to it with the handler that should set got response to true, and then just waits until that happens. In reality, though, this code will block forever. The reason is, as mentioned earlier, that our code is inside one of the blocking blocks of the flow. And until it exits, no events can be handled, including our fetch callback. We don't allow it to finish due to a blocking loop based on a variable that can never change because we don't allow it to finish. Deadlocks. Somewhat ironically, even real multithreading on the web doesn't solve this issue, but it's subject to the same limitations. In a native code, you can create a new thread and expect it to execute some code whenever it's ready. However, on the web, multithread is represented via a Walker API, which needs to asynchronously fetch a separate script before it creates a thread. And you guessed it, this requires a scheduled task. One that event loop will never get to execute if the main thread is blocked. So even if you want to create a new thread, you first need to finish execution on the current one and give control back. So in the provided very simple example above, you will never see the console log coming from the worker because the thread is just never created. Finally, even simple APIs like sleep that are synchronous in native code and allow to wait a specified number of seconds are also sort of an I/O. Sure, you could implement it in very straightforward manner that would block the current thread until the time expires. And in fact, that's exactly what Emscripten does in its default implementation of sleep. But that's very inefficient. It will block the entire UI. It won't allow any other events to get handled meanwhile. In general, just please don't do that. Instead, a more idiomatic version of such thing in JavaScript would involve calling a set timeout and subscribing with a handler to the point when the timer expires. What's common for all of these cases in different APIs is that you want to be able to take an idiomatic code in the source language, like the one on the left, that uses regular blocking synchronous APIs for any I/O, whether it's dealing with files, creating threads, or just sleeping, and somehow transform it into an equivalent of the code on the right that executes any initial code, then uses asynchronous API for I/O instead, by giving control back to the event loop, executing the rest when the I/O operation has finished. This is exactly where Asyncify comes in. Asyncify is a compile time feature introduced by Emscripten that allows to pause the entire program in an arbitrary place during its execution, save the entire state, includes the call stack and any temporary local variables, start an asynchronous operation, and later, when that operation is finished, resume from the exact same place and with the exact same state as if the program has never stopped. It's magic. This is quite similar to a sync-await feature in JavaScript that I have shown earlier, but unlike that one, doesn't require any special syntax or runtime support from the language, and instead it works with plain old synchronous functions. So how does it work? In a very simple pseudocode, if we take an example like this, where we have only one asynchronous call and no real state to store, Emscripten will take this code and transform it into something like the following. Here, the first time code is executed during a normal execution phase. Only the part leading up to async sleep will get evaluated. As soon as the asynchronous operation is scheduled, Emscripten will save all the locals and unwind the stack, while returning from each function all the way to the top until it returns to the browser event loop and gives control back. Then, once the async sleep resolves, Emscripten will call our function again, but this time in a different mode, variable set to rewinding, which will restore all the stored locals and evaluate only the part after the async sleep call, providing seamless execution as if the code was never stopped in the first place. How do we use this feature? If we wanted to implement an asynchronous sleep for the last example, we could do it like the following. First of all, emjs is a macro that allows defining JavaScript snippets as if they were C functions. Then inside, we use an API Asyncify handle sleep that tells Emscripten to suspend the program and provides a wake-up handler that should be called when the asynchronous operation has finished and code should resume. In our case, we pass that handler directly to the set timeout, but could be used in any other context that accepts callbacks. Finally, we call this async sleep function anywhere we want, just like regular sleep or any other. Then we need to tell Emscripten to activate the Asyncify feature when compiling the code. We do that by passing -s Asyncify. And we need to provide a list of functions that might be asynchronous. We do it by providing it in -s Asyncify imports array. This way, Emscripten will know that any calls to those functions might require saving and restoring the state, and will perform all the necessary transformations to inject the supporting code for that. Now, when you execute this code in the browser, you'll see a seamless output log, just like you would expect, with B coming after a short delay, and no UI being blocked. You can return values from Asyncify functions too. All you need to do is return the result of the handle sleep and pass the result to the wake-up callback. For example, if I wanted to fetch some numeric answer from a remote resource, I can use a snippet like above, and it will also seamlessly issue a request, suspend the C code, and resume once the response body is retrieved. In fact, for promise-based APIs like Fetch, you can even combine Asyncify with JavaScript feature async-await. Instead of Asyncify handle sleep, call Asyncify handle async. And then instead of getting a wake-up callback, you can pass an async JavaScript function and use regular await and return inside, making code look even more natural as synchronous, while not losing any of the benefits of an asynchronous I/O. But that still limits you only to numbers. What if you want to handle more complicated data? Say to read a response as a string, like remember our file reading examples. You can do that too. Emscripten provides a feature called embind that allows you to handle conversions between JavaScript and C++ values. And it has recently gained support for Asyncify as well. So you can get promises from JavaScript APIs like Fetch or any other, and call .await on them, quite similar to what you do in JavaScript, but with a different syntax. If you're using it this way, you don't even need to pass Asyncify imports as a compile flag. It will be taken care of you, since this is a built-in method. Now, this is all good and works great in Emscripten. What about other toolchains and languages? Let's say we have a similar synchronous call somewhere in our browser code, and we want to map it to an async API on the web. Turns out we can do it too. First of all, we define this function as a regular input. The Asyncify transform itself is completely toolchain agnostic and can transform literally any WebAssembly file produced by C, C++, Rust, AssemblyScript, any toolchain. It's shipped as part of WASM-op tool from the binary end toolchain. It's a WebAssembly optimizer and can be involved like on the slide. Similarly to the Emscripten invocation shown earlier, we pass --Asyncify to enable the transform itself, and then --pass arg to provide functions that should be treated as asynchronous points, where the program state should be saved and later restored and execution resumed. Now what we need is to provide a supporting runtime code that will actually do that, suspend and resume our code. For that, we have shipped a JavaScript wrapper, which you can find by the given link, or as Asyncify WASM on npm. It simulates a standard WebAssembly API, but under its own namespace. The difference is that under regular WebAssembly API, you can only provide synchronous functions as imports to your native code. But under the Asyncify wrapper, you can provide asynchronous imports as well. Once you try to call such asynchronous function from the WebAssembly side, in this case, async get answer, it will detect the return promise, suspend, and save the state of the entire WebAssembly application with all its locals and so on. Subscribe to the promise completion, and later, once it's resolved, it will seamlessly restore the whole stack and state and continue execution as if nothing happened. Since any function in the module might make an asynchronous call, all the exports become potentially asynchronous too, and they get trapped as well. So for example, you can call the instance exports main and await its result to know when the execution is truly finished and not just waiting on I/O. As one more example of third-party toolchain using Asyncify, Julia, a technical computing language, as they call themselves, uses Asyncify to bring its coroutine support to the web. Now I'd be happy to provide an example here, but I have never tried Julia myself, and I'm a bit reluctant to just copy-paste official examples, so if you're interested, go ahead and try it. Instead, let me move on from artificial examples altogether and show some real-world demos of things that become possible thanks to Asyncify. I've shown this slide before, describing various storages available on the web. And I mentioned that there is a new API, native file system, that allows to access an actual real user file system from a web application. On the other hand, I mentioned that there's a de facto standard for web I/O, including all sorts of file system operations. It's probably its largest part and use case, WASI. What if we could map one to another? Then we could compile any application in any source language with any toolchain supporting the WASI target and run it on the web in a secure sandbox context, while still allowing it to operate on real user files, just like it would when compiled to a native binary. The only issue with such mapping is that native file system uses asynchronous APIs and promises, whereas WASI uses synchronous I/O, more natural for native code. But as we have seen with Asyncify, it's no longer an issue. So I went ahead and did just that, mapping WASI APIs to native file system ones. And ideally, I would show you a live demo here, but I found out it broke about an hour before giving the presentation. So I'm glad I have it recorded instead. Let me just show that. I've added a couple of more features afterwards. But anyway, you can see how I'm able to select a real folder with some test files. And I'm using CoreUtils port to list all the files here, and I'm getting all their sizes, data, and so on. I can read the file's contents. I can copy one file to another, which shows how you can even write files also from WASI on the web. You can see that the content indeed becomes the same. I can delete files. Dangerous, but again, behaves just like a real native app. It all works. Now, this one I didn't try, so let me just stop here. I think this is pretty cool. But it's not limited just to timers and file systems either. You can go further and use other more niche APIs on the web. For example, also with the help of Asyncify, I was able to map libUSB, probably the most popular native library for working with USB devices, to a WebUSB API draft, which gives asynchronous API access to the USB devices on the web. Once mapped and compiled, I got standard libUSB tests and demos and examples to run against chosen devices right in the sandbox of the web page. Here you can see how it discovered my connected Canon camera and printed various internal information from the device, including the name and the manufacturer and other data. I think these examples are pretty cool, and they demonstrate just how powerful this tool can be for porting all sorts of native applications to the web, allowing you to gain cross-platform access, sandboxing, data security, all of this without losing any functionality of the native app. Of course, this talk wouldn't be complete without talking about downsides. Unfortunately, Asyncify Transform isn't completely free, since it has to inject quite a bit of supporting code for storing and restoring all of those locals, and navigating the call stack under different modes, and so on. It tries to modify only functions marked as asynchronous on the command line, as well as any of their potential callers, but that still results in average 50% overhead in terms of the code size. It's unfortunate, but in many cases might be acceptable, given the functionality you gain. One thing to keep in mind, though, is to always enable optimizations when compiling with Asyncify. The transform itself adds quite a lot of code. Most of it can be optimized the way WASM opt, but you need to remember to enable those optimizations. Otherwise, the binary end-up will be a lot larger. As WebAssembly develops, it gains new language-level features. For example, there are discussions of stack switching and coroutines, which would provide a more natural compilation target for Asyncify and should allow us to completely eliminate this overhead altogether. If you're interested in tracking such proposals and further development, you can subscribe to the WebAssembly design repo. Meanwhile, I think that Asyncify remains the best solution for bringing native applications to the web and seamlessly integrating with all sorts of asynchronous APIs. Here, there are some useful links, and I will, of course, include a link to the slide and post it on Twitter later, as well as to the demos. And thank you, and please contact me with any questions.